Hello everyone, this is Ryan Hong and this is my ENME351 Lab 5, Sensors with First Order Dynamics.
To get us started, I'm going to be analyzing this plot created in MATLAB. As you can see, we have two different time responses from two different resistors. The blue line, which represents the 10 kiloohm resistor, reaches steady state faster than the red line, which models the 100 kiloohm resistor. Resistance and time constant are directly proportional. The time constant equals the resistance times the capacitance. Therefore, the larger the resistance, the larger the time constant. Here's the code to my Arduino. As you can see, I used a digital pin to produce a voltage and two analog pins to read both the input voltage and voltage across the capacitor. After, I created a timing function using a while loop and millis function to continuously output 0 and 5 volts for a period of 10 tau. I was able to read the input and output voltages at a time interval of tau over 50. This is the circuit that I used. I used analog pins A1 and A2 and digital pin 2. To create the labels on my oscilloscope, I created a new function called oscilloscope, which draws lines and creates text. This function is called in the draw function of my processing code. This is what my oscilloscope looks like for the 10 kiloohm resistor. This is what my MATLAB plot looked like for the 10 kiloohm resistor. This is my oscilloscope for the 100 kiloohm resistor. Here is the MATLAB plot for the 100 kiloohm resistor. As you can see, the 100 kiloohm resistor takes longer to charge and discharge in comparison to the 10 kiloohm resistor, as mentioned. This is because the 10 kiloohm resistor has a lower time constant magnitude. Here's a thermistor that I am using for the temperature sensing portion of my lab. As you can see, the resistance is 10 kiloohms at a temperature of 25 degrees Celsius. Based on this value and the voltage divider equation given in the lab instructions, I concluded that the resistance is greatest when R is equal to 10 kiloohms. Here is my voltage divider circuit. I am using the 10 kiloohm resistor and thermistor. Additionally, I am using analog pin A2 to read the output voltage. To heat my thermistor, I am using this thin films heater as well as my finger. Additionally, I have changed my baud rates to 9600 in both my Arduino and processing code. This is my voltage at room temperature. Watch what happens when I heat the thermistor. The resistance increases, therefore the voltage decreases. My thermistor is back to room temperature. Watch what happens when I apply a cooling ice pack to the thermistor. As you can see, the resistance decreases, therefore the voltage increases. So does the thermistor circuit behave as intended? Yes, it does. This is my MATLAB plot when heat is applied to the thermistor. If you ignore the outliers, you can see that my plot does not oscillate the same way that a second-order sensor does. Here is my MATLAB plot for when the cooling ice pack is applied to the thermistor. Ignoring any outliers, you can see that the circuit behaves like a first-order system.
That was the end of my video everyone. If you enjoyed my video, please like and subscribe. Thank you.